good afternoon, everyone. I hope you have already recharged your energy to follow the next lecture by Premana and Premadi PhD. It's about introduction to cosmology. Okay, in this season, I think it will be similar with the previous season. So you can write your question or your comments in the chat box, and at the question and answer session, I would like to invite you to ask directly the speakers. And I have to remind you again about the Zoom etiquette. Please mute your microphone and turn off your video unless I allows you. And also, please give your full attention to the lecture and type your question in chat. And also you can raise your hand. And also do not annotate the slide, the presentation slide of from speakers. Okay, maybe I will hand over to Premana-san. Time is yours. Thanks.
Thank you, Anton. Thank you, everyone. Welcome back. As Anton said, hopefully we are all recharged. I realized I was a bit too slow in my first session, so to keep up with the expanding universe, I need to accelerate. So hopefully we'll cover what I intend to cover for these two lectures. Right, so I'll see my slide is showing, I hope.
Yes.
Excellent. So I'll just go through this very, very quickly. So when you have Einstein field equation, basically what you aim to get is a solution which tells you the geometry. And the geometry itself is described by how, in general, how would somebody see the distance between two nearby objects? And if you extend the distance between those two objects, how the what we call this distance element or line element would grow following the geometry of that particular space-time. So these three formulation of line elements are the mini distance between two very nearby objects in three very different geometry. So the first one, the blue one, is this flat geometry, and it could be quasi-flat, but it is something that people perceive as being flat. Second is what we call a closed geometry or with positive curvature, and you often associate that with a sphere or with a ball. Of course, a ball being a very, very limited view of a sphere. And then the next one is what we call an open space, a space with negative curvature, with peculiarity being that you have distance that is going larger and larger as the two objects that you're measuring the distance is also separating. So these three geometries are the generic geometries that Robertson and Walker are talking about, which could accommodate the cosmological principle that we saw before. So in addition to these three generic geometry, each of them should remain with the same value of curvature while the universe is changing its size. So universe could take any of these geometry, but as long as it changes its size, they cannot change its geometry. So once it picks up one geometry, it's going to stick with it for the rest of the history of the universe. So I will put that into our cosmological model, which we saw as the Friedman matter actuation. Now we rewrite it in a more compact form that I now reintroduce to you the right-hand side of the equation, which is the radiation term, the matter term, and the dark energy and the curvature. Now, we need to pay more attention on how A appears in each term. So for radiation, for example, it is divided by A to the 4 and matter by A to the 3 and so forth. Whereas the dark energy doesn't change with time, meaning the density of dark energy stays constant with time. Now, the difference between the radiation and matter on how they change their density could be explained by these cute pictures that Ryden put in her book, where in matter you have a number density, and each particular clump of matter associates with a particular energy. So you could just use m times c squared being the energy of each clump. And when the universe expands, so you just have the mc squared times the number of particles divided by the new volume, which is larger. Whereas with radiation, things is a little bit different, or very different rather. You have a number of photons, which is described by these screwy little things. But while the universe is expanding, the number of the photon might remain the same, but each of this wiggly thing, which tells you the wave nature of light, actually also expanding its stretch such that the energy of each photon lowers as the universe expands, and it lowers by this factor scale A. So therefore, the energy density of radiation goes down faster by 1 on A compared to the matter. So radiation remains contributing at the very early epoch of the universe, because if we put a number now, say 1, which is the common value people take as A for now, then if the universe is expanding, it means that in the previous time, A must be smaller than 1. So it could be that A has a very small value as such that A on 4 or something divided by A on 4 would be A to the power of 4 would be a very large number compared to the rest of the other terms. So a very early time, meaning at A very small, when A was very small, this first term dominates. Now, at some later time, these two terms would be comparable in size. And then just a little bit after that, this second term takes a turn to dominate, because this A to the power of 4 becoming quite large as such that this omega r, which is small in the first place compared to omega m, becomes very small. And then at a later time in the universe history, the second term dominates, which is called the matter domination era, and this is the radiation domination era. And currently, it seems like we are dominated by this dark energy, in which omega lambda, which doesn't go down with time, meaning that as the universe grows larger, they're becoming more and more of them, to make sure that the density remains constant. So since we could sort out this time in the universe history, what dominates when, so we could in particular try to solve this equation just one domination at a time, so just to see how things develop during that particular domination. And so that's a nice way of trying to get a solution of this simple looking equation, which otherwise is rather complicated if all the terms are, you know, alive with all this non-zero, and then they're comparable in size, then, you know, basically you need numerical computation to solve it. And another thing which is very nice is that radiation, matter, and dark energy have a different equation of state. That is the equation that relates pressure to density. And you know very well that pressure for radiation is 1/3 to the density of the of a photon, and then for matter, which is very very considered to be dust-like, you know, it's got very very low pressure, so the the motion of the particles is very much described by the speed of sound, which is very much less compared to the speed of light. So therefore, one could use zero as the pressure, so it's pressureless matter. Whereas for dark energy, you have a rather non-intuitive relation between matter and pressure. You got the more matter, or the more of the constituent you have, the larger, but in the negative, of the energy. So those are the different equation of state, which we'll put into this Friedman matter equation, and then trying to solve for A as a function of T, right? So let me see if I have time for that. I had prepared for one Einstein de Sitter, which I hope we could just go through very, very quickly. So Einstein de Sitter model is doesn't represent our observed universe, but it is you know, a very simple model, but also it's pedagogical to see how everything is derived from this compact Friedman matter equation. So let me see if I could just get rid of this notion. Right, so Einstein de Sitter model is a model where the geometry is flat, meaning K, the curvature is 0, and it is matter dominated, meaning all the constituent of the universe is matter. You don't have radiation, you don't have dark energy. So omega sub 0 is the total density of the universe right now. And since omega equals 1 relates with K equals 0, so all domination of matter, meaning omega naught equals omega m. So your Friedman equation is now become very, very simple. So all this thing, this term is gone, this term is gone, this term is gone, so that only this term remaining, and there's an a squared over here, so you got just one a remaining. So now your equation for energy gives you this a dot equals h naught times a to the minus half. Now this is a rather well-known differential equation that people have given ansatz for the solution has the form of this power law. So a should be a function of t with a, you know, t to the power of some number, with c being a constant of proportionality. So if you put this ansatz into this equation, you would get a solution which gives you how a evolves with time. So it is a rather simple form where t is to the power of 2/3. And if you put values for this equation with today's value, which is all agreed to take a as 1 for today, then right now the universe has this h. So the h of the universe today is 2 on 3 h naught. So depending on the value of h naught, so if you put H naught is 70 kilometer per second per megaparsec. You got a number of roughly 10 giga year, which is rather short. So therefore what I mentioned that this doesn't represent our observed universe, but it is a good way to understand the Premana model. Now, with this model, we would like to know how far out could we see. So that means the distance of the horizon today. So this is just 3 times c times t0, and t0 is that. So you got a number, and it's not a very big number. Meaning, if you don't have a large number for your horizon distance, meaning you cannot see further out. So the horizon distance is the limit within which you could see things. It is the longest distance that photon could propagate given the age of the universe, right? So with that also you could do some calculations. So if you're given a source, a galaxy at a particular redshift, then you can basically calculate the proper distance between us and that galaxy on 2 different times. First is at the time of observation. So once you see the galaxy, that means the photon reach you, then you could calculate the distance between that galaxy and us right now, the time of observation. But you could also calculate the distance between that galaxy and us when the photon just left that galaxy, so at the time of emission. So you could see it could be a very, very different value, depending on what? Depending on various things, among others is the H naught. So depending on the H naught, you could have a rather different proper distance between a galaxy and us at a particular Z, depending on the time observation or the time of emission. So in cosmology, it is imperative to add the time of a distance. If you ask a distance between a galaxy and us, then you must ask another information. Which or when do you want that distance? Do you want that distance at the observation time or the emission time? Because it could be, totally different value. Now, oops. Why is it? Oh, right. So those calculations look very nice. You could put numbers and you crank the values. But problem is, those are just models. They don't necessarily represent the real universe. So we have to have other ways to estimate distance, for example, or other things that we wish to measure about the universe. So those measurements should be dependent on those models. We should be able to find other methods that we could use to estimate distance, for example, without using the formulation that I just shown you. So those are the big homework that I mentioned in my first lecture. So, for example, just go back to distance, because distance is the big homework. So we'll try to concentrate on that. So cosmological distance is based on two different principles, and you could use that further. So one is called the angular diameter distance, and the other is called luminosity distance. So those are the principles. Now those principles are applied to be used on different objects, and then you sort of identify them as different methods of distance estimation. So depending on the objects that you use, you will encounter different challenges. So these are the list of various ways that people try to use while they try to estimate distance to very, very far objects. whatever method you choose, you definitely need to have something very bright as your source, because the farther the object, the dimmer they get. So you might want to have something extremely bright. So the except for the last one, gravitational lensing method, that perhaps Anton will mention, or somebody else in the subsequent lectures, they are all needing some kind of calibration, which I will tell you later. So therefore they constitute what we all call the cosmic distance ladder. I'll show you later. So, but now let's go back to the principle. So principle number one is using the comparison between the intrinsic brightness, the luminosity we call it, which is the energy that the particular source emits per unit time, say per second. And we compare that to the flux or the intensity of brightness that an observer sees at her or his place. So depending on the distance, so you assume that this source emits its energy isotropically. It's the same amount to all direction. So the further out you are, you need to divide that luminosity or that energy per second that the source emits onto a larger and larger surface of a sphere. So if you stand about this distance, then your patch right here only receive about 1/9 of this patch, because with the increasing distance, you need to do that. You need to square distance. So flux is luminosity divided by the surface of this spherical area. So the larger the radius, the larger the L, so the smaller f. So flux goes by distance square, distance to the -2. Right. So dl is now what we call the luminosity distance, as the square of L on 4 pi f. So basically, if you know your flux, and if you know the intrinsic brightness of the object, you could determine distance, and vice versa. If you know the distance and you measure the flux, you could calculate L. But the problem is you neither know dl nor L. So who would go to the galaxy and measure its luminosity at that location? So that's the problem. We have two unknowns in just one equation. The second principle is the comparison between an intrinsic size, which is, for example, the physical diameter of this galaxy. There's a nice Andromeda picture taken by our observatory staff, by the way, and compared to the angular diameter, which is the angular extension that this object makes seen by this observer. So that is measured in radian, so 2 pi radian over the circle. So this is just a fraction of a whole circle. So this is the relation between this physical diameter to the distance between the object and the observer. So of course, the larger the distance is, the smaller theta. So those are the main principles that people use in estimation, distance estimation. But again, in cosmology, things becoming much more complicated. The thing is the truth that we follow photon from its location, the source location to us. The photon travels through the universe to reach us, and through those travel, they could encounter various things. Could encounter area with very massive object, area with almost completely nothing. So Einstein said in area where you've got lots of mass, the volume or the space is curved by the existence of that mass. Meaning that curve also affects the trajectory of the photon, but such that the true distance is actually all those little steps that photon take from the source to us. So in general, we cannot have a formula. We don't know what the photon went through. So what we do here is just make an average of trajectories. So given a particular universe, you might expect, oh, there should be such number of galaxies. Some of them would have this mass or a distribution of mass, and then you put them together in the equation, and then you arrive with a formula. But in principle, no formula could describe each individual trajectory of a photon, which actually is the true distance. So now, using all those simplification of our model, we could arrive to some formulae, which again tells you the average distance between a source at a particular z to s. On average of the so if you put an arbitrary object at a particular z, it will not necessarily have this particular value. Okay, so this is what we call the matic relation. It tells you actually the relation between a flux and a distance, or magnitude with distance, magnitude in astronomical term, right? And for the two distance formulae for angular diameter distance and luminosity distance. Now, just because of the reason that I just mentioned to you, if you have two galaxies, one at Z1 and the other at Z2, with Z1 being less than Z2, and you wonder what would be the distance between the two of them. So the distance between two of them is basically you need to calculate one and calculate the other, but you cannot just you just cannot do this, like what we do in just flat geometry. So the distance, the angular distance between the two galaxies would be this. So this is the x. Remember our co-moving coordinate for Z2 for galaxy 2, and this is the co-moving coordinate for galaxy 1. And this is the secret recipe that tell you about all this cosmological parameter, gives you a particular model. Now, if we elaborate this recipe to our Einstein de Sitter universe, which I just mentioned to you, then they look rather simple. The matic relation for angular diameter distance and the luminosity distance are just this. So the difference is where 1 plus z appears in the equation. So luminosity distance gets bigger. It's a cone which starts, which apex is on the source, and it goes bigger to us. Whereas on angular diameter distance, the apex of the cone is at us, and it goes bigger towards the source. Okay, now on the various objects or phenomena that we use as a distance indicator. So this is us here on Earth, and this is going out to the deeper universe. So for a very small distance, object very nearby, you could use radar, and you could use parallax, trigonometric parallax, so using our annual motion around the sun. And for stars within the Milky Way, we could use the main sequence fitting, which is using stars which are on a particular stage of their evolution. There is main sequences where they spend most of their time being stars. and they usually have a very nice feature that people could just use and then calibrate. So, and then Cepheids. Cepheids are, I'll come back to that figure later. Cepheids are very interesting stars, very useful for us. They're variable stars with very tight period luminosity relation. So it seems like they go larger and smaller and larger, and, pulsating like that. And while doing so, they become brighter and dimmer and brighter and dimmer, and very, very periodic manner. And Henrietta Leavitt studied many, many of them and found that they have a very tight relation between its brightness and periodicity. So when they bright and dim and bright and dim, so it seems like the brighter they are, the longer their period is. So so if you have a galaxy that you know the distance, for example, I come back to this. So Andromeda, we know the distance because it's small enough, it's close enough that we could know its extension, but it's also got this Cepheids variable, that this is the a picture, a photo of Andromeda that Hubble took, and this is his scribbles that tells us, or tells him rather, how the period luminosity is appearing on Andromeda. So whenever you have a galaxy that you know the distance, then you could transfer between the observed magnitude or flux to the luminosity, which is the intrinsic value, the intrinsic energy. So then you know you have all these galaxies that you know the luminosity and you know the periodicity. So if you have a galaxy that you don't know the magnitude, you just plug in the period here, and you can find the luminosity, which is something that you might not know if you don't know the distance. So for example, a Cepheids with 30-day periodicity right here, you only have the flux, but you don't know the luminosity because you don't know the distance. But using this graph, you could borrow this graph to just go up there. So it's about 30 days, and then you go to the left and find that it's got a luminosity of 10,000 times the luminosity of the sun. So this is how useful Cepheids is. It's been very reliable, and because many galaxies nearby are estimated their distance by using Cepheids. So all is well, I think, that we have a Cepheids. Problem is, Cepheids is not bright enough that we could see them in farther out galaxies. We need something even much brighter than Cepheids. So we are sure that in faraway galaxies there are Cepheids as well, but they're already too dim for us to see, and let alone to follow their periodicity. So we need something even brighter. So that even brighter thing is supernovae. So supernovae is a phenomena at the end of a certain star evolution, whereby they explode. And the way they explode, in particular type 1a supernova, is so well-mannered, as such that we could understand the physical processes rather well compared to other type of supernovae, and also depending on their, and which we identify by their chemical elements learned by looking at their spectra. But also the way they explode is something which is amazingly uniform. So these are samples of supernova data, supernova type A. So you could see that they are just like normal stars or almost normal star, and suddenly they became very bright. Let me get my cursor on, became very bright, and then sort of trail off, and then, you know, get dim again, and then almost disappear practically. And all the supernovae show similar pattern in their light curve, in their way of showing the change of intensity from day to day. So the peak is when we figure the supernovae was exploding, but of course, you know, we observe the universe without knowing which star is going to explode when. So therefore, this is the trick part, and we don't have that many supernova exploding anyway. So we need to have a very good monitoring strategy. We sort of sweep all the sky and to try to observe as many type 1a supernovae as possible, and therefore we could compare their light curve feature, and then we put them together in a stack to see how far they are. So they all have the same shape, but the height of their light curve, this is the vertical axis is the brightness, and the observed brightness or apparent brightness. Of course, the dimmer they are, the farther they are, because the mechanism of their explosion is rather uniform. So you expect that their luminosity at the explosion is about the same. So you expect that the intrinsic value of this peak are the same. So the difference in the peak in the apparent magnitude would tell you the distance. So we use supernovae type A as a distance indicator for distant galaxies. So far, it's been very good, and people use that to farther and farther away galaxies. And this is a sample of an old accumulation of supernovae data that they put together in a Hubble diagram. This by Saul Permotel and friends. It's one of those teams that won the Nobel Prize, as it shows that the universe is not only expanding, but expanding with acceleration. So these are the examples of methods that people have used to estimate cosmological distances. What I mean by cosmological distances are distances which cover representative size of the universe. You can't use distance between Andromeda and Milky Way, for example, is cosmological because they are too close, and also Andromeda is blue shifting towards us rather than red shifting, meaning Milky Way and Andromeda are coming closing together rather than receding from each other. So we can't use the distance between Andromeda and Milky Way as cosmological indicator. Now, for further away galaxies, what are we going to do? We might not see enough supernovae. So that's when we rely on Hubble's law. We came back to a Hubble relation like this. So if you got something at the redshift of, or you know, we go further to right redshift of 5, for example, and we don't see anything, maybe gravitational lensing because it doesn't use this calibrating method, you might be able to estimate distance, but in general, you need to use the formula that the model gives you. So this is where things get tricky. You don't have enough independent method of estimating distance, and you rely on the model. So this is just a cartoon that standard ruler is the angular diameter distance, and the standard candle is something like Cepheid or supernovae. Now the cosmological distance ladder is something like this. This is a very well, it's a illustrating the trickiness of using cosmological distance, using calibration. If you have a galaxy with a Cepheid on it, you use the Cepheid to calculate the distance. And if you're very, very lucky, extremely lucky, to have a supernova on that same distance, on that same galaxy, you could calibrate the the supernovae distance to that of Cepheid. Now, if you have a even farther away galaxy, which doesn't have Cepheid or have Cepheid but you can't see, but have a supernovae, then the second galaxy distance is calibrated using two supernovae, supernovae on galaxy 1 and supernovae on galaxy 2. So those are the things. But if you have a galaxy which only have one Cepheid and then another galaxy only supernovae, then you have problem with calibrating. So sometimes you sort of brave yourself to do that because you various desperation drives people to do so. But this is what we mean by you need to be very, very careful. So if you have set a mistake on the first run, you bet you're going to get bigger mistake on the second and third and so forth. So you need to be very careful and make sure you know your distance that you estimated on the lower run are well determined. Right. So measuring the universe also or the distance also gives you an idea of the age, because if the universe has time to expand it much, then you know the other way around. If you have the size of the universe, you could perhaps estimate the age that or the time that it took to expand that much. Now the model, come back to the model, it gives you that the h naught to the -1 gives you some idea of the age. But if you put the model together, then you have something like this. You put all these omegas into it, and then you do your integration, and gives you the age at that particular that particular scale. So this equation tells you when the universe has size A, what was its age? Okay. Now, but on the other hand, we've got also objects in the universe which are old enough that we could use as a lower limit for the age of the universe. And among others, globular clusters. There are clusters, there are groups, a huge group of very old stars, and our own Milky Way have many of those. And since we have a good handle on how stars evolve, we could estimate the age of those stars. So it is logical to assume that the universe must be at least that old. Now, the other method that is still rarely used is the white dwarf cooling. So one particular star would, our sun might go through that in a later evolution stage. It wouldn't explode because it doesn't have enough mass to do that, but it just blow away, you know, its outer envelope, and the core would remain in it as a white dwarf star. It's a rather dim star, is very small, and things are still going on within, but you know, very slowly. But with time, the white dwarf would just cool down, and the amount of cooling down tells you the amount of time it has used to get that temperature. So then again, you know how much time a star would reach its white dwarf stage, and then in addition to that, the remaining white dwarf cools down and tells you some time span, and then it gives you another lower limit for the age of the universe. So what people do is compare the number that they got from the independent model, the independent method, with the model dependent one, and gives you, in a way, constraint of various things, but the easiest one would be the rate of expansion of the universe, which is h naught. Now, so there are other things that we need to measure. You know, the density we haven't talked about, how to measure. Those I would refer to other lectures. So the various, like I think Professor McGaw this morning talked about the scaling relation, probably Fisher and Faber-Jackson relation for galaxies, and then tell you the physical properties of the universe, and you compare that to what you observe, and then you have an idea of the not only the mass but also the distance to them. So those various things, please make sure you follow the other lectures. Okay, now I'm already delayed, so it's the second part of the lecture, how we perceive the large-scale structure and how they evolve and all that. So while the universe is expanding, since it expands in adiabatically, meaning it retains all the total energy, the energy doesn't go out, that and we don't all import energies from whatever is out, and we don't know what out means. So that means with the enlargement of the universe, the energy density goes down. Now, if we associate the energy density with temperature, that means that as the universe gets bigger, the temperature goes down. So the scale factor as a function of T is on a upside down manner with temperature. So the very good thing is now that we now have another physical parameter that doesn't appear on Friedmann-Lemaitre equation. This T simply comes in from thermodynamic consideration, being the universe being expanding in vertically. So the temperature is a really good new parameter that we could use further. Temperature could tell you what physical process is going on. So if temperature T relates with time or with scale factor as such as this, then we could guess what physical processes took place at a particular time or a particular scale. So this is extremely cool because then we could make a historical reconstruction of what might have gone through the universe history. So if the universe starts with something very, very small, so A is extremely small, T is just, the time when it starts, and as it expands, we could follow, okay, at this particular time is 10 to the minus 10 second, the energy is so big, 10 to the 15 Kelvin, or in giga electron volt it's about 100, and it continues to expand. I'll just pick up any particular interesting moment. It's about a few 100,000 years after the Big Bang. The universe has temperatures of a few thousand Kelvin only, and we know what might happen there. What might happen there is that electrons small enough energy that it could be bound by the nucleus of atom, such that they would remain by it for the rest of the universe history until there's another ionization period in the later time. But this is a very important moment. So I had mentioned that in answering one's question earlier, that so before then, the energy of the photon and the electron were so high that they interact very intensely. So whenever a photon goes this way, they would encounter an electron, would be deflected another way. So as the result, the photons could not propagate very far. So the photon remain in thermal baths together with matter. But when the energy was small enough, an electron could not escape from the nucleus, we have a neutral atom then, and there are much less free electrons going about to scatter photons. So photons could propagate freely, and those photons are what we call now the cosmic microwave background. So currently, or today, the temperature of the universe is about only 2.7 Kelvin, that represented by the cosmic microwave background energy. So this is very, very useful. Otherwise, so the relation between scale factor on time with the temperature tells you the relation between uh, um, uh, what physical processes could take place. So those are the various things that happen on the first 300 or 400,000 years after the Big Bang. I had explained CMB very quickly, so I'll try to be very quickly as well as the particle interaction. So the universe could have really high energy at the beginning, and we couldn't fathom the intensity of that particular time at the beginning of the universe. But we could do physics rather safely when the universe start to have a temperature around 10 to the 10 Kelvin, which is very high still, of course, compared to our standard now. But that's the time when we could be rather confident about what physics is going on. So what physics is going on when the universe has about this temperature, all these interactions, what we call interactions between a photon and electron positive or negative. So this gamma or photon, and the interaction between positive electron, negative electron that creates photon. This is the time when photons were created rather productively, and another family of particles, the neutrinos, also interact among each other and create pairs of electrons. Oh, so these interaction took place when the universe has a temperature about this. So T is about a few times 10 to the 10K. Now, what happened before that, you know, the temperature 10 to the 12, 10 to the 15, that would involve particles with higher mass. Particles with higher mass should be produced much earlier when the universe has higher energy. But at any rate, it's good enough that we know this, because this is the time when we could, as I mentioned, safely enough to do more physics. So this tells you the rate of success of interaction production. So how much photon would we expect by this pair production, for example? Well, depends on what's the temperature. When the temperature is high enough, so you got the right-hand side, you know, give you rather high value. Gamma is the rate of interaction, where H is the rate of expansion of the universe. So they're racing against each other. So the faster the universe expands, the faster it cools down. So the faster it cools down, you know, you get to lower temperature in such short time, such that you wouldn't have a good rate of success. So that's the idea. That's how we try to estimate the number of photons, the number of neutrino, the number of electron-positron scattering processes back then. So the photon itself, there's so many of them. So people estimate that the number ratio between baryon and photon matter and to photon is about 10 to the 9. So there's 10 to the 9 photon for a particle, a matter particle. Now, another interesting thing about photon is that they're distributed very nicely following this Planck energy distribution, which gives you a black body radiation. So it's basically a distribution of photon within an isolated volume, which the universe is, or at least that's what we assume. Universe is already everything in it. So it is all there is. So with that, the black body radiation is is a good system that describe how photon is distributed within it. So this is just a cartoon, of course. So this is the intensity of the number of photon in each particular bin of energy. So this is h time frequency, which is h, not the not the Hubble constant for 100. This is the Planck constant. This is the Boltzmann constant time the temperature. This is your way of measuring energy, and this is what we observed. So it's really lovely looking black body radiation feature. So, and with the peak at 2.7 Kelvin, so that tells you that the universe on average has a very low temperature, so 2.7 Kelvin. This is Kelvin, mind you, not Celsius, so it's very, very low temperature. Right, but before the CMB, far before the CMB, only the first 3 minutes of the universe, a very important reaction took place. This is when the nucleus of a very simple atom, the lightest atom, was created through nuclear reaction, meaning the constituent of nucleus got together and created atomic nucleus. Of course, the simplest one being hydrogen, it's got one proton. But if you have more constituent in the nucleus, then you basically either having a heavier nucleus of the same element, or you change to another a heavier element. So, for example, deuterium or deuteron, the nucleus of a deuterium consists of a proton and a neutron. So the number of proton tells you the uniqueness of the chemical element. So hydrogen has got one proton, but it could have an extra stuff in the nucleon. One neutron or two neutrons making it a heavier hydrogen. Like, for example, this a deuterium with one proton, one neutron. You add a neutron to it, you got a hydrogen with three constituents nucleon. The difference of the total mass is released in the product as photon. So you produce photon this way as well. Now, of course, this is a posteriorly looking. What we want to see, what is it that the universe could achieve at a certain time? So it seems that after only about 3 minutes, the universe achieved as far as making the nucleus of helium-4. Helium-4 having two proton and two neutron in its nucleus. And these are the various ways helium-4 was created. So I don't think I should go through the detail, but after that, the universe has gotten cool enough that further nucleosynthesis could not be achieved. That has to be wait until the stars are already formed. So you can imagine by Coulomb relation, particles with the same charge would repel. So proton and proton in the electromagnetic manner would repel each other. But how could they get together into heavier elements like helium and further very, very heavy elements like iron and oxygen and carbon that we all have in our body? That require very high temperature, very high speed that could collide them, then close enough that the strong force pick up. The strong force is much lighter compared to the Coulomb force, but they only work in a very, very close distance. So that could only happen when each of those particles have extremely high energy. So the universe could not retain that very high energy for very long. You know, it continues to expand, it continues to cool down. So at the most, the universe globally could create only helium-4. Now, that could be calculated very, very accurately. People very smart have done that, and they predict that at the most, universe could create about the amount of the helium that the universe could create globally would constitute only a quarter of the whole matter of the universe, the whole baryonic matter of the universe. And when they go out to the telescope and do lots of observation, and voila, that's what they found, that the abundance of helium-4 was about a quarter of what other baryon is. Now, another interesting thing is that if they vary the cosmological constant to see how different the yield would be if they vary the, for example, the baryon density, they would arrive at a rather interesting prediction about, if you move baryon from something very small to very large, then you got all these colorful stripes to give you the prediction of the amount of helium. Now, and deuterium. So what they see here is that the more baryon, the more proton and neutron there is in the universe, then the less deuterium would be left over. Most of them would be captured by one another to create helium nucleus. So if you have more baryon, you would expect to see more helium and less deuterium left over. And so this gives you an idea of how to use Big Bang nucleosynthesis to constrain the amount of baryon. So if you got omega m is the matter density, we don't know whether those matter fully consisted of baryon or not. Now we know that it's not. Baryon only contributing a very, very small percentage. But this observation tells you that it is true that the baryon density could not be very large, because this is the observation and this is the model predicted. So you could tell that the deuterium left over is just this. So you really don't have that much of a baryon at the beginning of the universe. So this is one of the first indication of the presence of non-baryonic matter in the universe, not by looking at galaxies, but by looking at processes that is happening in the very, very beginning of the universe. So this is entirely independent of the galaxies, which is very good if you want to see how dark matter is the idea of dark matter is evolved. You start with how people thought about missing mass in galaxies, but this is another view of constraining baryon by the early universe. So I think this is really, really a great addition to the cosmological development. Now, another thing about cosmic microwave background that I have not mentioned in the beginning is that how do we use it to tell us about the universe? So we know now that they're on average 2.7 Kelvin, but what else that we could extract from it? What we could extract from it is its non-uniformity. It is 2.7 Kelvin on average, but it actually shows very, very tiny fluctuations. The temperature 2.7, the fluctuations in the order to 10 to the minus 4. So extremely small, but those small fluctuation tells you a lot of things, and actually those what we need. Another thing is that the power spectrum, the feature that how they uh, they are not they are not uniform is depicted by what we call the power spectrum. This is the measure of the fluctuations on the temperature on various scales. And what is interesting is that those power spectrums, so this is a nice picture of a sample of a power spectrum of a of a cosmic microwave background. It depends a lot on the cosmological parameters. So that gives us an idea that we could vary our cosmological parameter and compare that to, and and then calculate the power spectrum and then compare it to the observed one, and then you discriminate cosmological model that way. So some cosmological parameters with certain values are just go straight to the bin because they are so very different from what is observed. But hopefully I will be able to tell you about this in our review session later this evening. Now, I hope I still have time. So now I like to show you very, very quickly the fluctuation in temperature on cosmic microwave background. Even though it's very small, it actually is the one of the most important thing that we need to know and have to see to answer the question, where did all these stars come from? How did galaxies form? They all need seeds to form, and those seeds manifest themselves in the very small uniformity in the temperature of the cosmic microwave background. So this is this is of course a patch of the cosmic microwave background temperature map, and the rest a simulation, except for this is also a picture of the observed universe. But in between are stages of gravitational clumping through the universe. So with time, so this is today and this is way back then when the universe was just releasing photon to propagate freely. So area which has a lower temperature on ZMB map turn out to correlate with smaller density. Area with higher have a higher density. So if you let that density uniformity to just evolve gravitationally with time, so area with larger than average density would clump together. Well, in the beginning, they would just expand slower compared to the rest of the universe. And the one that has higher density would eventually collapse. Remember, Joel mentioned yesterday the wild area and the tame area. So the tame area is where gravitation takes hold and letting everything clumping together gravitationally, whereas the wild areas where the universe is still expanding and gravitational interaction is much underpowered. So with that in mind, people try to do some calculations. So basically what we have again, you use total energy distribution in this way. It manifests as some mass conservation. This is the flow. When you have the universe expand, you consider it a fluid dynamics, and mass is conserved during those moments, and gives you what is called the continuity equation. How the density evolves with time is the gradient, or how the density or the mass or the momentum actually is dispersed around space. And the second one is the Euler equation. Euler equation tells you how velocity evolve, and velocity is something that we have to consider very, very carefully. When you think of a galaxy is moving, And actually, it could move by two things: by the Hubble expansion and by its own uh, attraction to the local system. So if the galaxy is a member of larger clusters, is a system of gravitational, so then the galaxy, this particular galaxy, would obediently move about the cluster in such a manner, such that what we measure as its velocity is a composite of its motion um, following the Hubble expansion plus its internal motion uh, following the gravitational system it is a member of. So we have this velocity of a particular thing, which is a Hubble motion, and it's what we call a peculiar motion. It's its own motion within its system. And another thing that we need is that if you have a motion, you have a change of motion, you need a force. That's what Newton said. But that force would need a source, and that source is described by this equation called the Poisson equation. So if you have a source, say with the density rho, then you have a disturbance, a uniformity by this rho on, along the space as much as this. So this is a compact way of writing that. So putting all those together, so the continuity equation and the velocity, the Euler equation, you have an equation that describes how velocity change with time. Well, time is actually attributed to this expansion of the universe. And if you do the same for the density, so density and velocity are the one that we are the two items that we allow to change from time to time. So the the density fluctuation changes with described by this equation after you linearize. You just keep the terms with just linear order. The higher order it could be very small because all the delta here are a small amount. They're just perturbance. The perturbance should be extremely small compared to the average value. So you just keep the higher value term, meaning the lowest order, and then you arrive at this equation, this second order differential equation, that gives you a solution which is very nice. So at any arbitrary time, the fluctuation, the contrast is contrast at some other time times some growth factor. So if this is an earlier time, so the later time, if the gravity works as this scheme tells you, then you get an overdensity, and this multiplication factor, and this multiplication factor again could be written in this differential equation form. So you solve for D, and then you multiply them into the contrast. And the D itself would depend on cosmological model. So each cosmological model gives you a different growth of overdensity, or in short, give you a different large-scale structure as a product. So I'll just give you an example of a cold dark matter that Joel mentioned yesterday. This is much earlier version of the simulation. So the earlier time is Z equals 50 all the way to now. So you see how the matter started nicely distributed, and then with time it just started to climb, and area with higher density would climb even more effectively. And now at the very end, you have matter clumps, and you've got and leave out lots of area with underdensity. So this is a newer a newer simulation using Lyman alpha hydrogen clouds, where you could see the dark matter, and then on top of that, the baryon that would light up the stars of galaxy, etc. But all this, of course, only use gravity as the driving force of the large scale structure. And this is very nice, meaning you don't put new physics into the large scale structure evolution scheme. You just have the Friedman, Robertson, Walker as the global arena, which is changing with time, just expanding. And within it, there are lots of physics going on, but the main thing is gravity, that putting things together and becoming the large scale structure, the cluster of galaxies and the stars. When it gets into this even smaller scale and you start talking about other forces, the electromagnetic, etc. So for the large scale structure, you could use gravity as your own backbone. So I think this too would be covered by other lecturers, so I won't go through very much. And I think this one too, perhaps there's CMB lectures or yeah. Let me see what the time is. Yeah, I think we are almost done. So I'll just put together what we have learned about the large-scale structure evolution, and I took this picture from Professor Premadi's talk yesterday, which summarized how the various structure scales from the very small to the largest. This is the mass scale. And from the small will be just very smooth a distribution of clouds, hydrogen clouds, to something very large, like a cluster of galaxies. And this tells you that the more massive they are, the smaller number they appear, meaning the less they are in number. And this is a similar graph, but with this the horizontal scale gives a different parameter, but it tells you about the same thing. It tells you about the scale, the size in space. So million light years, meaning light year is so 3 point. So 1 light year is 1 kiloparsec, 3 something light year. So at any rate, this horizontal scale is the size scale, spatial scale, where this is a mass. So you could do volume calculation real quick and then add some density and give you a mass scale. So what very nice is that all this span of very long scale, from a very diffuse one to the more compact one, they all fit in one curve like this, and that is an indication that the evolution scheme that started from the seed that we read off from the temperature fluctuation of CMB is could be used as a seed that we develop further, with the growth factor that I just introduced, into something which is very large, even as large as cluster of galaxies. So this is a huge encouragement for people to study how the evolution of structure came about. And as you see, we didn't use any fancy physics. It's the physics that we know. Of course, once we got into very much detail of all these things, then the interaction between the dark matter and the baryon could be rather complex, or among the baryons themselves could be very complex. But that's another matter. We're talking about large scale structure as an average feature of the universe, and it seems that we're doing all right in that thing. So I think I'll end that. I'll end it there, Anton, and perhaps take questions if there's any.
Okay, thanks, Dr. Premana. Okay, since we don't have much time, I'm try to look at the chat box. So there is so many questions for your lecture.
Oh, no.
So maybe I will prioritize for lecture only participants first. Maybe Bu Vaneswari, Kasi, are you there? Yeah, you asked so many questions. Maybe you can pick two of them and ask them directly. Okay, please.
Yeah, sure. Thank you, Professor. The talk was really good. I have two questions. Um, when omega gamma, omega cosmological constant that dominate, like described in Friedman equation, dominates the modified Friedman equation, the rate of change of A is proportional to A. We get that, right? So which means you get ever accelerating exponential growth, just like inflation.
Right.
So we explain inflation by Mexican hat style field. Can we explain today's universe using that, or is it simply the ground state of a vacuum that has small energy rather than zero energy of zero?
Let's see if I got your question correctly. Yeah, so if the dark energy dominates, which it could have in the very early epoch of the universe, it might be or has to do with the very short and very brief period of the inflation. But what about next part of the evolution? It seems that the dark energy could not have its full power dominating the Friedman equation after the end of the inflation epoch. Well, the success of the growth of structure tells you that the dark energy could not dominate for the length of the history, not even on long patches of its history, because otherwise, it would be very difficult for matter to clump. The H naught or the Hubble expansion will be too large. Even small example that I give you about the pair annihilation rate, the gamma
Yes.
on H. So if H is very, very large, the pair annihilation would not be successful. So, and then things went on from there. So that gives you a constraint on when dark energy could dominate.
What's your personal perspective about, like, does the universe expands forever, or we have a big crunch like the Big Bang?
Well, yeah. I think you could put in the favorite number for all the set of density of the cosmological parameters, and it gives you some prediction that the universe is going to expand forever, and it's not going to slow down. But whether it's going to expand within a smaller scale, that we don't know. We need to understand the nature of the dark energy itself. Whether it's going to grow stronger or it's going to go down, we don't know. But as it is now, it's going to expand forever.
That answers my question. I have one more question. How can we explain the universe moving from a state of nearly uniform temperature, that is the microwave cosmic background, to its very uneven structure like today, current universe?
Yeah, that's the steps that I tried to show you with this So the temperature fluctuation, people, the temperature fluctuation CMB is related to the density fluctuation at the time of the last scattering, when those photons were free, and that is called the Sachs-Wolfe relation. So delta T on T for temperature is about 1/3 of delta rho per rho. So the contrast in temperatures is comparable to the contrast of density at the time of the large scattering. So, and then those contrasts grow.
Yes, thank you so much, Professor. That answers my question.
Thank you.
Thank you.
Okay, thanks for Bufani's worry. And then there is some question about supernovae type 1A. So maybe I will call Suzu. Are you there? Suzu?
Yes, I'm here.
Yeah, maybe you can represent another question. Okay, please.
Okay. So, for the type 1A supernovae, as a standard candle, we know we can fix the further distance much further than our local universe. That last year, some people have done a paper about the how to say the color the type 1A supernovae at the in night curve, and when the night curve is rising, there are some difference in color. Using different filter, and they get two separate curves with some specific time. And my question is there any proper calculation only to fix to solve this problem as a standard candle?
Yeah, that is an issue that people still try to resolve on using supernovae type 1A for distance indicator, especially at a higher redshift. There's no, not yet a very super confident understanding on whether the mechanism of the explosion is the same. You know, the higher Z supernovae compared to the lower Z supernovae. Is there any evolution difference? Whether they start with the same kind of mass, the same mechanism. So there, people think that you know, the evolution matter should play minimal role, but if you go to further redshift, then you cannot be too confident about that. So I think if I got your question correctly, the multi-wave length probe, get you different curve could perhaps indicate that. So what people might do is just have more and more samples of high redshift supernovae to perhaps calibrate among themselves. You don't calibrate supernovae from high redshift to the very low redshift. They might have a evolution processes embedded in it. But if you calibrate supernovae among the same redshift, you might have a better handle of it. I think.
Okay, I think I got it.
Okay, okay.
And I got another tips on the on your slide, maybe the primordial nucleosynthesis part. Could you go back to that slide? I think you type a little bit wrong about nucleosynthesis.
Oh dear.
Okay.
Yes, yes.
So sorry, Suzu. Maybe because you are full participants, maybe you can ask that
Yeah.
question and on the next season after this. Okay.
Yeah, we could. Yeah,
okay.
but
Thanks.
thank you very much for
Okay,
Thank you,
spotting
thank
the
you,
mistake.
thank you.
Okay, maybe two questions more from Mrunalini. Okay, is there? Are you there, Mrunalini? No, Mrunalini. Yeah, maybe in previous season you asked something about the concept of the universe. Maybe you can ask here.
I asked about we have considered the first assumption was we considered the universe as a closed system. That means the energy is we are considering the conservation of energy. So how sure are we the energy is conserved? Do we have a model that the energy is conserved, that we are not interacting with the non-baryonic matter in any other way? Because this dark matter will interact only in terms of gravitation, not in any other way. But if there is anything like a phase mixing between the two states, the baryonic and non-baryonic, or any such.
I'm so sorry, but I'm afraid I could hardly hear you. Perhaps if you could speak slowly, or if you have written your question in the chat box,
Maybe,
let me see if I can find it.
Yeah, I have sent to your WhatsApp. So
Okay,
you can
let me
see
check. Okay, let me read what Anton forwarded to me. Is the concept of the universe as a closed system only an assumption and everything we know is built over it? Or is it a solution of observation? Right, of course it's an assumption. We don't know, and perhaps we cannot know what's beyond our observable universe. And perhaps what people often worry is that if they think of a closed universe, they think of a small universe, with a clear boundary and all that. But what Friedman universe is, it could be, a hugely sized universe, really, really huge. But it is already everything. It is all there is. So when the universe expands, it's not expanding to fill out an already existing space. It is actually expanding to create space, as the balloon that I showed you. If you look at the surface of the balloon, every time you add air into the balloon, you add area on the surface, the area which is not there before. But of course, the balloon itself, it's existing within a space, within our room, for example. But that is not our universe. The universe, so that actually help us understand that there is no special point in the universe. If there is if the universe is within a larger space, then its expansion should enable us to identify where it is expanding from, a center of the expansion, if you will. But there is no such thing. So of course it is an assumption, but there's also assumption based on a reasonable ideas of how things might have been. Of course, we could be very wrong about this, but if somebody asked about multiverse in the beginning. Of course, there could be other universe, but we don't have any access to them. So it's very hard to talk about them. When we talk about multiverse, for example, it is more on on ways to explain the various values that the universe has at its beginning. But for the purpose of our framework that we have talked today, what we have is adequate to set up this construction. So we, as I mentioned before, we are able to see how galaxies evolve from CMB, for example, from the overdensity that the CMB photons encounter. There, you know, that we detect in their temperature fluctuation. So so far we seem to be not needing information from without, from outside of the whatever is. So even saying outside is somehow I feel not right, because you know, you cannot say outside if everything about the universe is already here. So I think that's my answer to that. We could talk about that later if you like.
Okay, thanks, Dr. Premana. Yeah, I'm sorry, because we are limited by time. Maybe I have to stop here, and for participants still can ask her in the next session. Okay, before we stop, I will invite you to open your videos, and we'll take a picture as usual. Wait. Okay. Okay. Let me check for slides 1. Okay, Suzu. Do you wanna open your videos or not? Okay. Okay, I will start for taking picture. Okay, keep smile. Okay, 1, 2, 3. Okay, second slide. Okay, I will. Okay, done. Okay, let's open your microphone and let's say let's give big applause to Premana-san.
Thank you for your lecture.
Thank you for the lecture, Dr. Premana.
Thank you for the lecture.